What I'm going to do is I'm going to spin this around. And the question is, where do I need to let go so that it hits a spot on the board that I'm going to mark? And every time I do this, I feel like part of the tradition is for me to make the denial. I did not hit Scott, just to let you know. I was doing this a number of years ago when I taught middle school, something very similar to this. Scott was prone to exaggeration. I missed him by, I got closer to Scott than I intended, I will admit that. But I missed him by about this much, and Scott's reaction was, whoa! And that was first period. In the last period, someone came in and said, Dr. Fox, I heard you hit Scott this morning. No, I did not hit Scott.
So in your middle school, you electrocuted someone and you almost hit someone.
The electrocution was, decades earlier. It was, 20 years earlier.
You're on a winning streak for sure.
No one has died.
Yes.
All right, so if I'm standing here and I want the thing to hit that spot, if you're uncomfortable, that's fine. I have some control. You afraid I'm gonna start doing lore stories after there's the Jose and the lore story? Where do I let go in order to do that? So so that we have a common language here, when we draw an absolutely spectacular model, X is right there, and I'm going to be swinging around like this. I'm going to be swinging in this direction. So from a common language, if you said I should release it at 12 o'clock, that means I'm going to release it here. Release it at 6 o'clock here, 3, 9, and then everywhere in between. If one of you says to release it at 6 o'clock and someone says 6:01, I don't have enough control to differentiate between that.
I say 3 o'clock.
3 o'clock?
Mm-hmm.
Yeah.
Somewhere close there.
What about 2 o'clock?
Like-
Is that okay?
Like 2, 3, and 4 sounds right.
Between 2 and 3. Just somewhere in between.
Somewhere between 2 and 3?
Yeah, that sounds about right.
Anybody feeling different?
I feel like 6 o'clock.
6 o'clock?
Yeah.
Okay.
You trying to kill me?
It should go.
6 o'clock would be,
Yeah.
I'm facing down direction.
Okay.
Oh wait, so if you're going to release it at the time.
I'm facing, so 6 o'clock would be there. So when it's here, I let go. You're the safest one in
Wait, I
here.
feel like I'm the one that's gonna get hit.
Was that?
It's gonna be easily.
All right. Any others before we
Actually,
risk Orr's life? The first semester I was doing this, we didn't have the rubber stoppers yet, and so I grabbed another bit of mass, those slotted masses, the 10 gram or 20 gram ones that have little
Oh
holes in
my
them.
gosh.
So we were using those, and the string broke.
Oh.
So I'm sitting there at the desk, and all of a sudden there's this, as it goes flying across the room. No one was hurt, because otherwise that would be a different story that I would be telling. It smacked into the board, so fortunately no one was hurt, but that's part of the reason why I'm checking the string, but it is a rubber stopper, so we put a bit of safety there.
Okay.
But, it hits you in the temple. Good luck. All right. It depends on how safe you feel with mind control here. But I'm gonna first do the 6 o'clock. I let it go when it's here. Now, because of control, I'm not gonna be zipping around really fast because I'm gonna do it somewhat slowly so that I can time it better. 3, 2, 1, go.
Okay.
Oh, okay. Interesting. So it was 6 o'clock?
Thank you for your faith. Although I would not have been insulted had you not had faith. All right, so 3 o'clock is here. It's going to be somewhere between 2 and 3, but let's see. 1, 2, I'd go just a little bit too soon.
Wait, so it goes linearly as soon as you let it go.
What did I do I lost the thing at the bottom.
Like just, yeah.
There you
Ah,
go.
There it is.
There it is.
I was thinking one of those things changed. So that's 3, that would be 132, somewhere around here. 3, 2, 1. So it's somewhere in that range. All right, so once I released it, what are the forces acting on it?
Well, just gravity at that point. Gravitational force.
Looks-
Gravitational force?
Yes. Otherwise known as, in this situation,
Acceleration due to gravity?
The-
Wait, no? Wait,
rotation.
wait.
Yeah. So, in which direction is the weight acting on it?
Down.
Yeah. So by Newton's second law, F equals ma, the force, the total force has to be in the direction of, or the acceleration has to be in the direction of the total force. So if the only force acting on it is down, what will be the direction of acceleration?
Yeah.
It's a projectile motion problem. So there is nothing to cause it to accelerate to the sides. And remember, if there's no acceleration in a particular direction, that means that the velocity does not change. In other words, the speed in that direction, as well as the direction itself, will not change. So the only direction it should fall, should go after I let go would be downwards. Which is one of the reasons I put the X here as opposed to up here, because I know it's going to fall some. So if there is acceleration, because it wasn't traveling in a straight line before, because as soon as I let go, it should travel pretty much in a plane, in a straight enough line, ignoring the fact that it falls, which tells me that the direction that this thing is moving in changes as it goes in a circle, which tells me velocity changes, which tells me there's acceleration. And the question is, what is the magnitude of that acceleration? If you've had physics, presumably you remember. If you haven't had physics, then that's one if you've listened to the tales from the elders in your tribe. Because presumably your grandparents have sung songs about this. I'm not getting any looks of recognition. Okay. Oh, so I did lose this. Where's the? Oh. There we go. So what we're going to do is take a look at an object that's traveling in a circle. It helps if I actually have the marker point. There we go. So there's my circle. There's the center of my circle right there, and this is a point directly in line with the center of the circle. And we'll establish I hat, J hat. Let's have this object that's being spun in a circle clockwise. So at some point here, we have the object traveling at some speed v, at this angle theta. And there's going to be a symmetric point over here where it's traveling at some angle theta here. And I am assuming a constant speed. So we're trying to figure out what is the acceleration because of change in direction. This is a right angle, because if it's traveling in a circle, then a tangent line should be perpendicular to a radius. So this angle here would be the complement of theta, theta prime. So since that's a right triangle, this angle down here would be theta. I know that acceleration is the change in velocity over the change in time. Which is just v final minus v initial divided by time. Well, let's figure out what VF and VI are. So if I've got my vector V here, I'm breaking up into perpendicular components, what would this side here be?
That'll be v sine theta.
Or
V cos theta.
cosine. That's my angle, theta is right here.
Oh,
That's the
okay.
adjacent side. So my final velocity is going to be v cosine theta I hat minus v sine theta j hat. That's my final, minus my initial. Well, it's pretty much the same thing, but it's flipped vertically. So minus v cosine theta I hat plus v sine theta j hat divided by time. And what does that simplify into? Or into what does that simplify?
1.
You.
Hold on. Cosine squared. Cosine squared. Just v. Right?
V squared sine theta.
Say it again.
V squared sine theta.
Said v squared?
No. 2v sine theta.
Oh, two, yeah. Sorry. One little thing that you missed.
J hat.
Oh.
Okay, yeah, that too, and
Meter. No, this is.
negative.
Oh.
So this is equal to, so my acceleration is equal to negative 2v sine theta j hat divided by time. Questions up to there, because we're gonna take a small little detour and then come back.
Wait, I thought. Oh, wait, never mind. Got it.
And that is supposed to be a negative sign, not a teardrop falling on the table. All right. Okay. What do you know about radians?
One radian is the length of is the radius essentially, right?
Of what?
Of the circle.
One radian would not. It is a.
Wait, it's not it's equivalent to the radius in the sense that it's the segment of the circumference that is equidistant to the radius.
The words, the syntax is not making sense to me. I think you're right on the right track. That just the words are.
I'm trying to find the
Strange.
words.
It's equal to pi, like 1 radian is equal to pi, right?
No, not that exact, but pi does pop into this. All right. In the 1800s primarily, there was a big push to get rid of all of the man-made, as much human intervention into math as possible. They wanted to come down to, is there anything that is just, seems to be true regardless of what any human has done? Which means we have to get rid of 360 degrees. From where does 360 degrees come from? What group? Or
Humans.
people?
People.
Babylonians.
Oh.
Babylonians had something special about the number 60. And if you think about it, it makes sense. I mean, if you're doing math, a base 60 system does have some common sense to it. And the fact that it is divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. It's got a whole bunch of stuff that will go into it nicely. And because 60 was particularly special to them, they somehow connected it with their religion. And they also saw a circle as sort of a perfect shape. And so if I break this circle up into equilateral triangles, yes, I understand it's flat here and it's curved there, but close enough. It's like your game piece in Trivial Pursuit. Equilateral triangle was special, and for an equilateral triangle, well, let's connect the two. Let's make each of these 60. And if I take 6 of these things, they can go around in a circle there, and so therefore we have 360 units in a circle, and at some point they became degrees. Obviously, man-made. There was nothing particularly special about 60, at least was thought by the time they came around to do this. What they did notice, and this sort of gets towards what was being said before, is that for any circle, every circle has a radius. If I take that radius and I wrap it around the outside, that angle is the same. Any circle, I take its radius, I wrap it around the side, and it basically creates an angle that is the same for every single circle. That is a radian. So the question is, how many radians are there in a circle? Well, what is the circumference of a circle?
2 pi.
What is the circumference of a circle?
2 by r.
Yes, 2 pi times the radius. So I have 2 pi radii going around the circle. Therefore, I have 2 pi radians going around a circle. So therefore, 2 pi radians, this is where the pi comes in, is what used to be called 360 degrees. Oh, we're gonna take a small little pause here. I'm just gonna let that run because pictures of the board should be enough to entertain people.
What I miss? A new unit.
Have several of us almost died.
Wait, what?
It was bringing like a metal, how do I say metal? Like a stopper
This
around.
thing.
Yeah,
It's going like this and letting it go.
yeah. And then he shared about how he almost hit a kid in middle school. That's important.
Robin and I did not have faith.
Mhm.
So I see you guys almost dealt with that. That's cool. Yeah, not much people do. All right. Enough rejoicing with this. Now, ultimately, there's a relationship between this angle here and the length around an edge. They're directly proportional. And so we come up with a relationship here that the arc length, S, is just going to be R times whatever the angle is in radians. Sort of think of this as standing room only, but that's my own mental thing. S equals R theta. The arc length around the edge is equal to the radius times the angle if it's in radians. Well, if I'm back over in the circle over here, the arc length is the distance from here to here. The angle is 2 theta, because each of those is theta. So that distance, as well as traveling at speed v for some amount of time t, so the arc length here is going to just be vt. So that is my arc length. My radius is, well, whatever that radius is there. And the angle is 2 theta. So I have vt is equal to r 2 theta.
is it VT?
I'm traveling at a constant speed for however much time it takes to get from here to here, for that amount of time.
So the whole arc then between initial and final velocity?
Yes, yes, absolutely. So therefore, V is equal to R2 theta over T. So if I plug that in there, my acceleration, negative J hat is the direction, and I've got two, I feel like I lost something here, just a second. S equals R theta, the S is the arc length, R2 theta. Oh, my problem is I don't want to substitute for V, I want to substitute for time. Time is equal to 2R theta divided by V. Plugging that in, we get negative 2V sine theta divided by 2R theta over V. The 2's cancel out conveniently. I get this V right here popping up on top, and so I end up with negative J hat times V squared sine theta over R theta. We're not done yet, but at least we've gotten rid of an unknown.
I just got lost between plugging in.
Okay, are you good here?
No.
Okay, so I took this equation here,
Mhm.
I brought the J hat out
Which is
front, just,
acceleration.
yeah, this is acceleration. Acceleration equals this. And then using my relationship between angle, radius, and arc length, I kept an equation for time, plug that into here.
Okay, I see, okay,
Okay, good to go?
yes.
Other questions?
Is that 2R theta over V? Or is that like,
That's right here,
yeah.
or same here, 2R theta over V. Yes.
So the VT equals S is velocity times time equals side? Is that correct?
This is just, the arc length is the distance that this thing traveled,
Yeah.
which is
Also-
just speed times